Okay, so it's a great pleasure to have Vishnu Jejjala here, and he's going to tell us about machine learning, the topology, and geometry of the number.
All right, so it's great to be here. Thanks for having me. Well, I'll tell you about some work I've been doing lately, last 8 years or so, on applying machine learning to Calabi-Yau manifolds. So I'll tell you some work about topology and some work about geometry. So I often give the talk with the title Precision String Phenomenology. So I asked ChatGPT, what does this title mean? And here's an image provided of precision string phenomenology. And there's another one. So these things can do really well with simple prompts. So I'll tell you about the story about string compactification, basically. So this is all textbook material. So the idea is that you get a four-dimensional n=1 effective field theory by compactifying the E8 cross E8 heterotic string on a Calabi-Yau field. So the Calabi-Yau is a complex scalar manifold which admits a Ricci-flat metric whenever the first Chern class vanishes. And these were conjectured to exist by Calabi and proven to exist by Yau. In addition to the Calabi-Yau manifold, you put structures on top. So you put a vector bundle on top, and depending on the rank of the vector bundle, you can break one of the E8 cross E8, one of the E8s in E8 cross E8 to E6 or SO10 or SO5. These are all known as grandification groups that embed the structure of the standard model. You can break the gauge symmetry further with freely acting Wilson lines and get exactly the standard model group. So ever since Candelas started with Strominger and Witten in the mid-1980s, this is sort of the textbook paradigm for string model building. So if you open volume 2 of Green, Schwartz, and Witten, this is what you'll see. So the Calabi-Yaus we have to choose from, there are lots and lots of possibilities. This goes under various names. It's the landscape problem or the vacuum selection problem, or all these things determine exactly how you get the known particle physics from that Amaditio string construction. And so far, this problem's unsolved. So we'd like to make some steps towards this, and some of the work we've been doing enables us to make some progress on this long-standing question. I'll tell you about polytopes in a bit. I'll talk about a lot about polytopes soon. So let me just explain what the words I mentioned actually mean. So let me define a complex manifold. Complex manifold is one where the coordinates are complex, and the transition functions between the different charts that form your atlas are holomorphic. So if these complex manifolds are endowed with a Hermitian metric, and just like in Riemann normal coordinates, you pick a point P on your manifold, you can choose coordinates the metric is flat, and the first derivatives vanish. You can't always do this in a complex manifold. When you can do this, the manifold is scaling. So the vanishing first Chern class means the Ricci form is exact, and the manifold is spin. So when the first Chern class vanishes, the second Stiefel-Whitney class also vanishes. As a result, you're allowed to have spin structures, which is what you want for fermions in your low energy effective theory. So the first Chern class essentially measures the topological twisting of a bundle on top, a vector bundle on top, and the vanishing of this, according to Yau's theorem, ensures that this Ricci-flat metric exists. So once we do this compactification in 4 dimensions, we have this n=1 effective field theory, and the Lagrangian consists of kinetic terms, which are in the Kähler potential. The Kähler potential is not holomorphic. It's a function of both phi and phi dagger, whereas the superpotential is holomorphic. It's a function only of phi. And in the superpotential, you have interactions between the fields. In particular, you have cubic interactions. The topological data about the Calabi-Yau gives us some aspects of the energy effective theory. It tells us what fields are present. It tells us what types of interactions they have. And in this manner, starting with papers in 2005, there are now roughly 1 million heterotic standard model constructions possible to X3D1s. So you get the standard model gauge group, matter charged the proper way under the standard model gauge group, the right sorts of interactions you expect to see in the Lagrangian, and that's all you get from topology. Yes?
What by data?
By data, I mean the fields in your low energy effective theory and how they interact. By topological data, I mean Hodge numbers, interpolarization numbers, and things like that. Yes?
So then you could explain about this like this, where we have, so when we talk about this Calabi-Yau, these are very tiny and curved.
Yes.
So what do we mean by symmetric?
Well, a torus is also a curved manifold in the same sense, but it admits a metric which is flat. I'll show you what I mean in a few more slides, but if you have the same question in a few slides, please ask again. I'll try to explain again.
RIT.
Yeah, it's right. So you can have the Riemann tensor not vanishing, but the Ricci tensor vanishes spaces. Okay, so the couplings that you need to determine how strongly the fields interact, these lambda IJKs in the superpotential, those are Yukawa couplings. And in order to calculate these in a general context, you should know the Calabi-Yau. You can know some structures on top of the Calabi-Yau, these holomorphic vector bundles, and you can know the Ricci-flat metric you put on the Calabi-Yau manifold.
So in the end, after the Calabi-Yau compactification, n is equal to 1 symmetry is preserved.
Yes.
At the standard model. That's the symmetry.
This is a setup. The naive compactification preserves n equals 1 supersymmetry. This is another reason why we want the Ricci flatness. The solution to the classical equations of motion preserves supersymmetry with Ricci flatness. If you put a different metric on, it won't be n equals 1.
I think part of the question was how are we going to get the standard model if it preserves it? How? What is the?
We don't know about that.
What is it?
We don't know how to. Once we get the supersymmetric Standard model, how you break this to the real Standard model? I don't have anything to say there. That's also somewhat model dependent in how you engineer SUSY breaking. We don't have. We're agnostic on that at this point.
Don't you get n equals to 2? Some cases or
You can enhance these things in some cases, maybe, but generically it's n equals 1.
So can one imagine these models as realistic models where instead, so from Planck scale we come down to some intermediate scale where it's preserved and then some dynamical or something.
You can imagine something like that, and in fact, that's sort of what we're envisioning. And I'll show you at the end of the talk that you sort of see things like hierarchies and Yukawa couplings already emerging in this n equals 1 story. So that may be some indication that these hierarchies we see in the physical spectrum is a consequence of a mechanism like this.
So these lambda ideas, since they're holomorphic data, are there some contexts in which you don't need to know the full metric to calculate?
Yes, and I'll show you those contexts.
Yeah.
Okay, so why do we need the Ricci-flat metric? Ricci-flat metric is the one that solves the vacuum Einstein equation speeding order. For the purposes of phenomenology, you need to normalize the kinetic terms in the Kähler potential. You need the Ricci-flat metric to do that. Yukawa couplings that I mentioned, the generic compactification, you need to know the flat metric to generate these because they end up coming from harmonic structures. And to write down the harmonic structures, you need the metric. I'm not going to say anything about moduli stabilization, but eventually you'll need to understand geometric details in order to stabilize the moduli. And then if you want to consider more complicated models, offer time corrections and so on, and address SUSY breaking, you need to know geometric features of the manifold. Ricci flatness itself is a system of fourth order nonlinear partial differential equations. So you write down the derivative of log det of the metric in order to get condition for Ricci flatness. Yau, in his proof, showed that this is equivalent to second order Monge-Ampere system, and he showed the existence of the solution. So his solution of the Calabi condition was non-constructive. So Yau doesn't tell us what the actual Ricci-flat metric is, he just tells us it exists. So today, the best we can do is a numerical approximation for Calabi-Yau's complex dimension and bigger than or equal to 2. What's known analytically? There are two things that are known analytically. One is the Calabi-Yau one-fold, that's the torus. So the torus has an area, which is a Kähler parameter, it tells us about the size of the geometry, and it has a complex structure parameter, the shape.
Statement about the uniqueness of the Ricci-flat metric
There's a unique Ricci-flat metric in each Kähler class.
in each Kähler class.
Yes.
But as you vary the moduli, this will change, right?
Yes.
You will
So if you change the complex structure moduli,
Yeah.
you're getting a degree as a new geometry. And in each Kähler class, that geometry is Ricci-flat metric as well. So you can see how the Ricci-flat metric evolves as you change the complex structure moduli.
Each scalar plus.
So the scalar parameter here is the area of the torus, and the complex structure
So why
parameter.
did you say each complex structure class also?
Sure, I can say that too. So I think I said that there's a unique Ricci-flat metric for any complex
Yes.
class. So the shape of the torus is this angle tau, which defines a fundamental region in the complex plane. So you get periodic boundary conditions like an old school video game with the top and the bottom, left and the right. This is the fundamental domain. And the metric on the complex plane is just dz bar. And to realize this on the torus itself, it took Clifford until 1873 to do this. So even the simple torus, which people have been looking at as a mathematical object forever, the Ricci-flat metric wasn't written down until the late 19th century. In K3, which is the two-dimensional, two complex dimensional Calabi-Yau, in a particular singular locus where things look Kummer surface, T4 mod Z2, Kochner and collaborators wrote down a Canada analytic metric. We compare, in principle, our numerical calculations to the analytic metric there, but it turns out our numerics are worst at this particular singular point. So the comparison isn't very good. But there is a analytic metric that's written down for the Kummer surface. As far as I'm aware, is the only two results for compact Calabi-Yaus that are known. For non-compact Calabi-Yaus, the Ricci-flat metrics that are written down.
Something on this slide is supposed to tell me about what the metric is. The fact that it's written as this polynomial equation is supposed to tell me what the metric is, or
No, this is the description of the Kummer surface. Yeah. So there's nothing about the metric other than the references.
can it not inherit the metric from P3? This when it's embedding.
Sure, it inherits a metric, but it won't be Ricci-flat.
That's not the.
Yeah. So if you just take a torus, for example, embedded in R3, the pullback of the R3 metric from the torus won't be a flat metric.
Not maybe R3, but there is this embedding in P2.
We'll start with that. That metric is called the BD metric, P2. That gets pulled back to the seed metric we'll start out with when you're finding the Ricci-flat metric.
Right, that's fine.
Yes.
How to read this number, the 1, 1, 1 and 1?
So, right, so these are the so-called Hodge numbers, they're topological invariants. This tells us there's, this is H00, H10, H01, and H11. This tells us about the kinds of forms you'll see in this kind of space. So in particular, there's a 20 here. If you look at this equation, it's a quartic equation in P3. So you look, write down all the kinds of quartic terms. So for example, Z1, Z2, Z3, Z4, it's a quartic term I haven't written here. If you count the number of quartic terms you can write down in terms of the 4 variables on P3, you'll find the 35 of them. If you take that 35 and you remove the GL force C redundancy, that takes you down to 19. That 19 plus 1 for the size of K3 is this 20 that appears here. Okay, so the 19 are called complex structure parameters, and that 1 that's left over is a Kähler parameter for the area. Volume would be K3.
So for the torus, I mean, is it like serious? It should be some straightforward metric, right?
It is a straightforward metric.
In the XY coordinate, for example.
Yes. I mean, this metric is just dz bar. Okay. But writing down dz bar in these torus coordinates, that was Clifford in 1873. So that wasn't obvious. So in order to do this right now, we do Weierstrass math, you lift a curve to the fundamental domain, and then the fundamental domain will get this metric dz bar, we pull that back. So it's relatively easy to do. It just wasn't done until late.
It's just the change of coordinates that makes X and Y periodic.
Okay, so I'll use neural networks to briefly summarize what these things are. We take some vector space, we map it to a different vector space. That's this function f, which accomplishes that map. So so we go from Rn to another Rn, and we have a vector here mapping to a vector here. This vector is really a vector which is acted upon by some nonlinear function element wise. So we take this vector, we then move it from here to here by acting the weight matrix, and maybe we shift by a bias. After we do that, we act as nonlinearity. A typical nonlinearity is this rectified linear unit. So it's just x times theta of x, for theta of x that means that theta function. And we just multiply each of these elements in this vector. We just act on this with a signal. Then we iterate this process. The number of times we iterate this is depth of the neural network, and the dimensions, these vector spaces, is the width of each layer in the neural network. So we can put this in a diagram, and we have some input vector passing on through a series of layers acted upon by these nonlinearities, and the number of layers is the depth, the length, the size of each layer is the width, and we can think about some output. For example, you just take the sum of all the elements of the vector of the final layer and call that our output. We want to compare this output to the true answer if we happen to know it. The true answer is often called the ground truth in this game. And we tune the elements of the weight matrices of bias vectors in order to minimize a loss function that describes the difference between the prediction of the neural network and the true answer. So in doing this training and minimizing this loss function, we use backpropagation, which is a fancy way of saying chain rule, in order to propagate what differences would in the answer make when we go backwards with the neural network. So combining backpropagation with the structure enables us to make predictions in many different contexts. And famously, this was awarded a prize in last year for Hopfield and Hinton for essentially developing this backpropagation idea and apply system mechanics ideas to Mr. Boltzmann machines in developing story about neural networks. But the neural network idea itself dates back to the 1940s, 1950s. So this is an old construct in computer science that had this renaissance in the 80s.
So you constructed the neural network yourself?
Yes.
What is NI? What is the size of the vector space for you?
Typically 100-dimensional, not very big.
What's the depth?
3 layers typically.
If the size of the neuron in a particular layer has to be greater than smaller than the previous layer?
No, it's not. It can be anything. So sometimes you want to bottleneck things in order to distill a high-dimensional information space into a lower-dimensional space. So it depends on the problem you're solving, and it's some trial and error involved in finding a good network architecture for your task.
So you have something like 10,000 parameters.
Yeah. Okay,
So
so
you use this nonlinear function like that.
we use the ReLU function, yes.
The lack of differentiability in the zero doesn't bother you.
You can sort of smooth this out. You typically use modified version that is slightly smoother. You can use a tangent function, you can use lots of different functions that generally have the same shape, and they all work.
And you are looking for Ricci-flat metric, right? So something nice and smooth. So
It turns out this doesn't matter. The optimization algorithms that people have constructed take care of these kind of solvents.
Well, I thought the data is very limited. I mean, you may be explaining, so you're gonna tell us what.
Yeah. Okay, so I'll tell you first about machine learning topology in order to show that we can apply these ideas to Calabi-Yaus. Then I'll come back to the geometry story. So there are some Calabi-Yaus which are particularly simple, a complete intersection of polynomial equations. If you want to consider the complete intersection of polynomial equations give you K3, there are 9 such constructions you can make in products of vector space. In the case of Calabi-Yau threefolds, it turns out there are 7,890 complete intersection Calabi-Yaus. So when this data set was produced, it was essentially one of the first big data sets in string theory. So these complete intersection Calabi-Yaus were essentially given to us by.
Remind me what I used to know this, but what is complete? What does complete mean? The completed solution.
It means you take the you take a bunch of polynomial equations
Co-dimension is
where they all intersect. In the sense that the solution that you choose is a zero all these different equations. It's a zero locus with a bunch of equations.
Co-dimension also has to be the same as the number of relations.
So this is the first condition, the sum of the dimensions of projective spaces minus number of equations we have is 3, typical big intersection. The C1 equals 0 condition is a restriction on the elements which appear in this configuration matrix. And this is condition, the sum of each of these rows is the dimension plus 1. So when you do this, you get 7,890 solutions. The first few solutions are the quintic. You take P4 with a quintic equation of P4. We have 4 minus 1 equals 3, satisfying the intersection condition, and 5 equals 4 plus 1, satisfying the C1 equals 0 condition. Similarly, you can write down a bunch of these different equations in a single projective space. You can also do products of projective space as well. And I've written down the Euler character of these geometries.
So what are the Qs?
These Qs are just the integers in these configuration matrices. These Qs are the 5s, the 3s, and so on.
Okay, what are these from the topology?
So they're telling you the degree of the equation. So, for example, for the quintic, it's a 5th degree equation according to P4.
Why is there like a, see here you just had a one row of numbers, but now there's the matrix of the numbers?
Sure. So, for example, you could take something like
Oh, it's intersection.
the intersection. Yeah.
So in the P and one, you consider the D. Sorry, why are there 2 numbers in the row then? 3, 3, for example,
There are 2 cubic equations.
or 2 cubic equations.
Three-
No, but
two-
that's okay. That's your intersection then.
Yeah.
Then what is this?
So let me write down another more complicated example. We take 3, 0, 0, 3, 1, 1. In basically 3. So I take coordinates here. So I have x, I, x, j, k, with some numbers combined. Plus some numbers here, yi, yj, yk. This equals 0, this equals 0, and xi, yj. So these are the 3 equations I read off from this matrix. So these are coordinates on this P3, these are coordinates on this P3, and this is the bilinear the coordinates on these 2 different P3s.
Oh, I see. So the vertical is telling me the degree in each variable.
Yes,
So each column is one equation.
yes.
Each column is one. Okay.
And P3 is CP3, right? Like
Yes, I mean, yes.
Sorry, the locus of solution for all these equations is the math.
Is the math thing we're considering? Yes.
That's a very basic question. Why are there a finite number? Why can't I just take higher degree polynomials? So, I mean, if I'm
Condition there.
Because you have the C1 condition. You first time
vanishes. Yes, okay.
Why is that the C1 condition? C1 equal to 0 condition in the quick?
There's no quick explanation. That's what it turns out.
The NR was what here? The thing now.
The dimensions of the derivatives. So here we have 2 different topological invariants, H11 and H21. H11 and H21, they respectively count the number of 2 cycles and 4 cycles, number of 3 cycles in geometry. These correspond to Taylor and complex structure deformations of 2, 4. One is size, the other is shape. The Euler character, based on the entries in this configuration matrix, is easily learned. So it turns out the cubic polynomial in the numbers that appear here. But for example, minus 200 is given by essentially the entries of this matrix in some combination. So you have this 5 is 4 plus 1, this 5 is 5 cubed, and we have this 5 again in front, and there's a 1/3 here, which is threefold. And this gives us minus 200. This guy here, we have 3 times 3, just 5 here. We have 5 plus 1, which is 6, minus 3 cubed, minus 3 cubed. Again, 1/3, minus 144. So there's a relatively easy way of calculating chi just from knowing the entries here. So you give all these 7,890 matrices to a computer, and it'll learn this formula that predict chi with essentially 100% accuracy.
Sorry, in your example here, why? How do we know it was x1? So this could be any cubic polynomial in X.
Yes.
And that's a modulus of them. Yeah. I see.
just like for the K3 here, I wrote down the quartic pieces and squares with quadratics, but I can also write down C1, C2, C3, C4, and so on.
Right. So each of these, is it just your number labels the different topological classes?
Yes.
But each of these comes with a large moduli space.
Yes.
This can be fundamental and of its first theory, right? With some param with some potential.
Yes. Right. So chi is easily learned. What about the actual Hodge numbers themselves? So in the case of these Calabi-Yau threefolds, the Euler character is twice the difference of H11 and H21. So you can read off the Euler character by knowing these other Hodge numbers. Similarly, you can read off all the Hodge numbers by knowing the other Hodge number and the Euler character. So we'll learn H11. These are the possible values of H11, 27,890 theoretical geometries. These are the values of H21. So you see the H21 range is much larger than the H11 range. H1 goes from 0 to 19, basically. So we'll learn these. And the way we often do these experiments in machine learning is we take 80% of our data set for training, and we use the complementary 20% for testing after the training process is finished. That's a standard benchmark machine learning people like to use. So if you train with 80% of the data and you use a neural network, you're able to learn the Hodge number H11 with about 85–90% accuracy. So these are the experiments we did in 2018, 2019. Since then, people have essentially used more complicated network architectures to get 100% accuracy in these experiments. So the Hodge numbers is something you can very easily learn using neural networks.
So did you explain why chi is the right thing to learn as opposed to?
Well, I mean, I just said that chi is something which is easily learned. So
Why is that? Because it's a formula.
there's a formula for it that you can write down. It's in Hooch, Calabi-Yau, for example. In that sense, we know what the answer is, but we don't remember what these numbers are. The formula turns out to be cubic in these numbers. So it's a relatively easy formula to learn. Yes.
Do we have similar formula for the Hodge numbers as well?
We have more complicated formulas. They're not, I wouldn't say they're simple, but there are ways to calculate this knowing figure eight matrix. Yes.
In particular, the complex number of complex structure moduli you can count by just counting how many polynomials.
Yeah.
So what was 70 at 90? With that 7,890?
The number of matrices to satisfy these conditions. They range from 1 by 1, the quintic, to 12 by 15.
The topological inequivalent classes of Calabi-Yau, right? Or not?
These are topologically inequivalent classes of clean intersections Calabi-Yaus.
Or some threefolds.
Of threefolds, yes.
I see. So just if you allow for larger and larger embeddings and more equations to narrow it
Yes.
out, it still is that
Still this number.
because of
Yes.
these constraints. Yes.
So if you change this 3 to a 2, and you try to do a similar story, only 9 solutions to write them down. It's an exercise, but you can do it.
So this is a very particular kind of Calabi-Yau.
Very particular kind of Calabi-Yau. It's not the most generic Calabi-Yau. I'll talk about more generic Calabi-Yau soon, but this is the first data set we looked at.
But is it believed that that topological classification is finite even for the most general set of Calabi-Yau?
It is believed but not proven. I'll say a few words about that.
Somewhat specific because all of these are intersections in CP.
They're complete intersections.
Complete sense against CP as opposed to
Yes, so it's supposed to be particle intersections. Yeah.
right?
As opposed to something which is less rigorous, some less constrained system with Okay, so we can machine learn the Hodge numbers. And we can look at larger data sets. So I'll explain what a reflexive polytope is momentarily, but I'll just say it's some polyhedron in higher dimensions from now.
Sorry, Vishnu.
Yeah.
How many of these 7,890 you use to train and to very?
I use different fractions. So this is the fraction used for training. The number which is reported typically is 80% fraction for training.
And the input is that matrix.
The input is just this matrix. It's flattened into a vector. Okay, so I'll tell you more about this polytopes momentarily, but let's just say there are certain polyhedra with certain properties. Starting from these polyhedra.
I'm sorry, Rajat already asked this, but you have analytic formulae for all of these.
Yes.
Features, right?
Yes.
Okay. And that is your training data.
That's our training data.
Yeah.
So we use this flattened matrix, and then we tell it what the answer is for 80%. And we test how well it does on the complementary 20%.
Okay. So this is a trial case where you know the answer, you want to see how it does.
And the formulas for these H's are also some simple polynomial.
They're not simple. They're not, they're very complicated expressions you can write. You can derive this from the matrix. You can also derive this using sequence chasing in the usual Meyer-Berry-Torres algebraic topology sense. You can also get this using Grubner basis algorithms, computational algebraic geometry. They're packages that calculate these things. As the matrix size increases, the complexity of calculation becomes doubly exponential, the size of the matrix. So it's not an easy calculation, but you can do it.
The formulas for chi, I suppose there is no error in a formula for chi, right?
There are no errors here at all.
But for these Wash numbers, there must be some errors for the function itself.
No, we know the answer. We know the answer exactly.
This complicated function, there's no.
Yeah, we've got this complicated Calabi-Yau. We can do the sequence chasing, or we can use this Grubner basis calculation. We get a number. That number is the answer. It tells you how many holes there are in various dimensions. That can't be something which is variable.
So there's no error.
There's no error here.
Just Macaulay 2 would do it.
Yeah, Macaulay 2 does this. This is the reason why mathematical data sets are nice. There's no error in the data set.
For instance, number of complex structure moduli is just some very simple thing, right? It's just counting how many polynomials of given degree.
Modulo rotations.
Yeah.
Okay. So we have this second class. These are so-called choric Calabi-Yaus. There's a algebraic chorus in the game somewhere. And these arise from monopolar reflexive polytopes, which we'll tell you about momentarily. It turns out there are 4,319 reflexive polytopes in 3 dimensions. They all give us K3. This K3 is a unique Calabi-Yau twofold. And then there are 500 million reflexive polytopes in 4 dimensions. The Hodge numbers are plotted on this plot with a heat map. They're focused at 2727. That's where the peak of this map is. There are 30,108 unique pairs, H11 and H21. So there are at least that many Calabi-Yaus. In fact, there are a lot more than that. That's already we know from topological data that there are a multiplicity of Calabi-Yaus in 3 dimensions.
So now you're looking at more general kind of
Yes.
Yeah.
Okay, so we found that
K3 is a unique Calabi-Yau in 2 dimensions.
all K3s are diffeomorphism equivalent to each other as real manifolds. This is something Witwatersrand showed.
And what was the 9 in passing mentioned?
There are 9 different ways of embedding this same manifold in positive projective space.
But then this 9 is an overcount? Or you get
These 9 are all
complex,
diffeomorphism equivalent.
but they're not complex structures. So you can just take any one of them and you get everything they want.
Yes.
Right.
But we need to replace your files.
I'll get there. The next slide or two, I'll get there.
So that means the 7,890 number also is redundant, would be redundant, that there are actually similar things there.
Yes. No, those are all unique as well. Those, wait, no, you're right. There are redundancies in some list. Okay, so there are new formulae for the Euler characteristics we can write down based on the number of features these polytopes. So the number of points on the polytope, the number of points on a dual polytope, the number of points on twice scaled up version of these gives us some new formula that we found. Per Berglund, his student Ben Campbell, and I found for the Euler character of these Calabi-Yau threefolds. And once we just got a bunch of data and we figured out which features of the data looked at most strongly, we did regression based on those features, came up with this formula. So we could have come up with a formula just by regression. We didn't know which features to look at though. So the machine told us these are the things to look at, write down the formula, then we're able to prove this.
So what do you mean these are the things to look at? Please?
So I take these polytopes I give various properties of polytopes and I feed this into some neural network. Then I ask which features of the input have the largest gradients.
So which matter for
which matter the most for the calculation. So I use a saliency analysis to figure out the important features, and then I do regression of the features and I found a max formula.
But do you really need a neural network for it? I mean, this is kind of standard, right? Like,
I didn't need a neural network for that, but I didn't know to use these features though, right? I just
but you can standard regression.
yeah, you could do that. Yeah.
Yeah.
But this is something which was accidentally discovered by machine learning. Machine learning was not crucial for this at all.
I missed what L was.
L is the number of points on this polytope, and L is the number of points this circle is dual polytope. These are twice scaled up versions of these. I don't know what the twice scaled up thing means physically. I just know if I feed it this information, it comes up with this formula.
Oh.
But I don't know what the physical interpretation of this guy is.
But you can derive it now.
Now I can derive this formula. Now that I know what it is, we can sit down and show this is the correct formula for the order curve. Similarly, there were new analytic results.
Was there an old formula for this? Was there some other formula known?
Yeah, sure. There are other formulas there now. These are all calculated. So these are calculated previously.
But
usually using governor-based tests.
But is this somehow simpler than the earlier formula?
It's as simple as the simplest existing formula. It's not any different or better. It's just a new formula.
No, but the formula is in terms of L, in terms of these points.
If you just knew the number of points of the dual, that's not enough to figure this out. You need some other data. And so the other data people have used before, I use this data. L is the number of points. Counts the number of points on a polytope. So I'll show you some pictures in 2D. Where I'll show you
And delta again, I'm so sorry, but delta was what?
delta is the polytope.
So what does 2 delta mean?
2 delta is a twice scaled up version.
Twice scaled up.
Similarly, people have come up with other analytic results, like the one I just wrote in bundle cohomology on surfaces and on Calabi-Yaus, using machine learning as a discovery tool in the pipeline. But afterwards, once you have a formula, you show the formula, and you don't need the machine learning. So one of the lessons here, maybe there are new ways to calculate things in algebraic geometry. Whatever the machine is doing in predicting Hodge numbers, for example, it's not doing what I would do by hand. It's not sequence chasing. It's not doing Grosvenor basis calculation. It's scaling polynomially rather than doubling exponentially with the size of the configuration matrix. So it's doing something different. So it suggests there may be simpler formula we just don't know for algebraic geometry of Calabi-Yaus. So this is suggestive, but we don't know what these formulae are. It's hard to open up a black box to figure this out generally. In some cases, for example, some knot theory stuff that I did with Onkar and Arjun Kar, we're able to actually, after we had our initial machine learning result, we were then able to figure out, using a saliency analysis similar to what I described, figure out the important features and come up with some analytic explanation of what's happening. But it's often the case you can't do this. It's just a black box, which gives you the right answer, but it's hard to figure out what's happening under the hood.
And are mathematicians interested in formulae like this? Do they find these formulae particularly interesting? Or?
I mean, they're sort of interested in such formulae that exist they didn't know about before. But is it revolutionary? No, it's not. Yes.
Just a simple query. Usually, machine learning, if I'm not wrong, there's an error in predicting some result, right?
Yes.
Then how come the machine learning this box is able to get exact formula? There has to be some.
Sometimes it makes exact predictions. It depends on the problem you're asking. If it makes an exact prediction with no error, that's suggesting that there is an actual formula to write down that you can then go look for.
It's not like a yes or no question, right? It's not like a classifier. It's like you have to fit an exact function.
Yes.
Then how come it's giving you exact formula?
Some things are simple, deceptively simple maybe. It turns out that if you make a prediction of say H11 and H21, there are error bars associated with those predictions. So that those calculations, there isn't a simple formula of this type based on the data we fed in. But for this particular quantity, this chi, there was an exact formula. And it figured it out that made the predictions exactly based on these data.
The neural network you're using doesn't have any stochasticity. It's just like a deterministic thing.
There's initialization. When you initialize the neural network, you figure out initial values, the components of the weight matrices,
Yes.
and the bias vectors. You typically draw that from just some distribution.
Yes.
Each time you run your network, it'll draw the different numbers. So there's different initialization. But once you initialize, then it's deterministic.
Yeah, like in LLMs, there's still stochasticity at the end, right? Like
Yeah.
where it can output different things each time,
Yeah.
even with the same input. After you've learned it, it's just deterministic in that
Yes.
sense.
Yeah.
So, when you were trying to learn guys from these L's of this sort, you were getting results that are extremely close to the right answer, and that's what led you to
Yes,
suspect that there may be an.
that's right.
So that should be the kind of a code smoking gun of some sort of a formula that you see that it's learning it very nicely.
It's learning it with essentially 100% accuracy every time. There has to be something it's learning from. Okay, so I mentioned reflexive polytopes. So what's a reflexive polytope? Reflexive polytope is a polyhedron with a single interior point, the origin. And all the different facets of this polytope are at unit distance from the origin. So I drew two examples in the plane of reflexive polytopes. So the triangle here, all these lines, there's a 1 on the right-hand side, it's distance 1. And similarly for the square, these are all distance 1. There's a single point, the origin. It turns out there's 16 reflexive polytopes in 2 dimensions. And these were known to the Italian school in the late 1800s. So this classification of reflexive polytopes in 2D dates back to classical geometry.
So sorry, I was spacing out. You're telling us about polytopes?
Reflexive polytopes.
Ah.
So a reflexive polytope is a polytope whose facets are at unit distance from the origin.
Polytope is like something.
It's like polyhedron, the shape. So the lines are all x plus y equals 1, x minus 2y equals 1.
It's like a triangle or
Yeah.
quadrilateral or something.
Yeah.
Okay, fine.
So there are 16 such polytopes that are reflexive in the plane. They all have a single interior point. That's the other definition. That's the other aspect of a reflexive polytope. It's only the origin inside. The polytope, if it's reflexive, its dual polytope is also reflexive. Okay?
So you define reflexive completely. One more. What was reflexive?
Reflexive means distance 1 and single interior point.
Sorry, this is L1 distance. What kind of distance?
I mean, the equations are defining this. The right-hand side is 1. The lines are, x plus y equals 1, x minus 2y equals 1, so on.
That's not distance 1, right? What is 1 exactly?
Distance to the base.
Distance to the face, I see 1 over square root.
Right. So maybe distance is the wrong word I'm using.
That all the equation should be ax plus by square root 1.
Yeah.
And why there are a finite number of tools?
Yeah, you can just do anything you want, right?
There's a single interior point. That's the other constraint you've got.
Single integer interior point.
Lattice. There's a
They're all
lattice.
lattice points.
Oh.
They're all lattice polytopes.
They have to intersect.
The vertex has to be on some.
The vertices are all, sorry, I didn't say that. The vertices are all integer points.
Dual,
Sorry?
you said dual, what is dual?
The dual, you replace the edge with a point. And you draw the, you take the midpoint of the edge, put a point there, and you draw the dual. Just like, when you have a dual to the cube, you get the octahedron by replacing the faces with vertices and so on.
But that lives in a scaled down version of the lattice.
Yes.
What is reflexive? Sorry.
Reflexive is the condition that you have the equation ax plus by equals 1. 1 is part of the definition of reflexive. And there's a single interior point, the origin. And all the points, all the vertices are lattice points.
Which in particular means that A and B are integers.
Yes.
And so with the dual, the origin stays fixed. That stays up.
Yes. Yes.
their distance will be up.
You can scale it up. There's also a rescaling you do. But yes, that's essentially how you get these dual polytopes.
Just one.
Yeah.
Why there are finite number of these? Was that?
If you could draw a 17th, it'd be very exciting to see. There are only 16 of these to satisfy the conditions.
We try to make them bigger than it should forward.
Yeah.
Just tell the origin as the medium.
Okay, so all these 16 polytopes that are reflexive in 2D, they all give you the torus when you make this Calabi-Yau. So you start with these lattice polytopes, and then you convert this to a Calabi-Yau space by following a prescription that Dr. Evan Borisov developed. So there's a procedure, start from such a polytope and write down the geometry.
Abhijit had explained that, mentioned that in the case of these CPs, we understand we get this Calabi-Yau from H linear sigma.
Yes.
So something like that here.
Well, I just write down some equation here. This zero locus equation turns out to have first term class action.
I was wondering whether there was a physics.
Physics reason?
Whether there's.
It's not entirely obvious.
Is when we find the dual lattice, like the midpoint of the edge might not be a integer.
You scale things up.
Scale
Yeah.
things up such a.
Yeah.
Will be hard.
So there are 16 in 2D, there are 4,019 in 3D, there are this 500 million in 4D. In 5D, so-called maximal polytopes have been written. There are about 185 million maximal polytopes. We don't know the total number of reflexive polytopes. Some numerology that Scholler and Skarka did suggests this is about a 10 to the 18. So it's not something you can ever tabulate.
Sorry, how do I go from how do I read off the dimensionality of the Calabi-Yau from the polytope?
It's so the polytope is 2D, you have a one complex dimensional Calabi-Yau. It's 3D, you have a two complex dimensional Calabi-Yau, so on.
Nice. And 3D once again is points are on a cubic lattice.
Yes. The same story. So for example, you just take this polytope here, add a point 1 up and 1 below. That will be a lattice polytope, which is reflexive. But there are other reflexive polytopes you can do, which you don't build from lower dimensional polytope.
What is story variety?
So yeah, so if you take let's see, you take okay, 2. Then we'll say this. So the toric varieties are geometries in which there's an action of an algebraic force. It turns out these toric varieties, because they have certain properties, they're interesting to mathematicians. So mathematicians study these toric geometries all the time.
Are they torus vibrations over a base manifold?
In the simplest case, yes, but they needn't be. They can have more complicated torus actions. But yes, in the simplest case, think about torus vibration.
These polytopes in some sense related to this toric, what is it called? Toric diagram?
Yeah, so you start with these polytopes, you build a toric fan out of this. The toric fan, you then have some hypersurface associated to that toric fan. That hypersurface, you take the anticanonical bundle, and that turns out to be Calabi-Yau.
Toric varieties we get F theory are torus vibrations.
Yes. Okay, so we don't know, as I said, all the Calabi-Yau. So Kreutzer and Skarka calculated this 500 million polytope list in 4D. So that polytope list is complete. We don't have a similar completeness in 5D. So I use machine learning in order to find new polytopes in 5D. So in order to do this, I'll use something called a genetic algorithm. So what I do is I take each of the vertices in my polytope and I convert this into a bit string. So I take these vertices and then I make strings of zeros and ones out of these. So for example, here's a polytope in 2D. It's got 5 different vertices. These are the coordinates of the vertices. And then I take these points and flatten this into a vector, and then I subtract the minimum in order to make these all positive numbers, and I convert these to binary, and then I just string them together. This gives me a representation of this polytope in terms of zeros and ones. So that's my population in a genetic sense.
Sorry, this is 5 dimension and 2 points.
This is 2-dimensional. There are 5 vertices.
5 points.
Yeah.
Sorry, what is this bit listing? How are you mapping this to what?
So I take this set of vertices and I flatten this into a vector.
Okay, just you take.
Okay. Then I subtract out the minimum element. So then I get positive numbers here. I convert these to binary and I just string them together. And I make sure that each of these is 1, for example, 0, 0, 1. It's a 3-bit number.
So the final output is it unique if you take a unique vertex?
Yes.
So unique.
Yeah.
1-to-1 map.
Yes. So this is the bit string associated to this matrix. Right? So then I take these polytopes and I ask how close am I to being reflexive? So I have some fitness score. So this IP delta is 1 if there's a single interior point and 0 otherwise. Then I look at how far away the facets are from being distance 1 away, in the sense we talked about previously. And I just weight these appropriately.
So how do you, I mean, the d equal to 1 condition, I'm getting confused. Because now that you have just the points, how do you see whether it's distance 1 or not?
You draw the points. You can use, yeah. So this fitness score is 0 maximally. It's 0 if I'm reflexive, and it's negative otherwise. Okay, so I maximize my fitness. So I take these elements of my population, then I rank them based on how close they are to being 0. Then I pick some random point along a pair of these, and then I swap based on, say, the left side of this random point picked. This is a selection of crossover, a la genetics. I do some breeding here among members of my population. And then I do some mutations. I take some 1s and turn them into 0s, or 0s and turn them into 1s. And then I have a new population, which I rank again, and I repeat this process.
This population is generated. How did you generate the population?
You generate some random variable polytopes. So this mimics evolution. So I'm happy to have Darwin and references. So Turing realized this had happened in the mid-50s, actually, and then people implemented this idea. So we were going to try to generate new reflexive polytopes based on this method.
So selection.
Yeah.
And this is what I don't understand. People use various things according to their this thing, but what exactly drives you towards this and not a neural network?
Each 5-year-old networks didn't work.
Yeah. So what does that mean about the question?
I don't know there's a principled answer to that. In that if I hand you a problem, is there a particular tool that solves that problem? Often you don't know. Often you've seen similar problems before when you apply some method you've seen before to a similar problem to this new problem. But there isn't really a toolkit that lets you know which is the appropriate thing to do.
So neural network didn't work. You said let's try this, and somehow it worked.
Yeah.
It might as well not have worked, right?
It might as well not have worked. We're going to try something else after that. So here's, for example, a polytope that I start out with randomly. It's not reflexive.
Selection and crossover once again, please say. So you rank, I understand.
I rank.
Then
I just pick a random point along this this guy here, for example, this place here,
Left.
and then I just split the first two members of the population by exchanging this bit with that bit, or vice versa. So this is like breeding. This is like your kid, your parents' DNA.
Okay, great. Then there is some random mutation.
Yeah.
And you go back. And you go back and select it. You right click.
Yeah.
And then your final output will be the guys that are 0.
Yes.
So the aim would be to have the top ranking members to obey that fitness,
Yes.
right?
Yes.
So
So
the mutations, are they correlated? So this mutation at one
uncorrelated.
uncorrelated.
There's some mutation rate that you put in as part of your architecture.
And completely independent of the selection.
Yes,
Crossovers.
yes.
Completely independent.
And it turns out you actually need the mutation. You just ignore the mutation. It's usually much slower to convert these to the right answer.
But do you have any intuitive sense as to why this algorithm for this problem?
No, I'll show you that there's another problem that we'll discuss soon, where there are two different ways to solve it. We solved it one way, some other group solved it another way. So oftentimes you can solve these things in more than one way.
Is there a discreteness that somehow, I don't know, I mean, is this it seems like it, lends itself to this genetic thing in a more natural way somehow.
Yeah.
I don't know how to say it.
The fact that you have a bit string means that there's this DNA-like feature that you can exploit, but it's not always the case. So it turns out to work for this particular case.
So I guess locality, right? Locality.
Yes.
And why exactly machine learning is coming over?
This all fits into the broad group of machine learning. I'm not sure. There's no. Go ahead.
How do you terminate this process?
You just stop after a while, or you find when things are zero fitness, then they're a reflexive polytope.
No, but how do you do that?
Take those away, right?
You take
Once
those
you've got a
away,
0,
yeah,
that you're
yeah,
done
yeah.
with that. And then you keep going with
Nice
that.
scope, no? So I mean, if you breed fit people, you will get fit babies. Why don't you use them for breeding also?
Maybe you should use that for weight, but you don't change those.
So you don't take them away,
Yeah,
you
yeah.
keep them in the population.
Sure, you use that too. I mean, I forget the exact details of what we did, but we found a number of examples as well.
And you have to get what is the rate of getting answers
I get that.
depending on
Next slide. Okay, so we also need to show, so this is some random thing we start with. There are a bunch of interior points, this is not reflexive. But we know that this polytope is the same as this polytope. And if you permute the vertices and you act with a GLN transformation on the vertices, you get an equivalent polytope. So you need to account for this equivalence as well.
So it's cyclically permuted.
So, well, not cyclically, you just trade a vertex with another vertex.
Why wouldn't you just get lines intersecting each other if you just
Sometimes when you do these things, you don't get a good polytope.
Oh, because these lines are drawn later on.
Yeah.
Once you get those, then you just make it convex.
Right, yes.
Okay.
Reflexive polytope has to be convex, right? It can't be a star shape.
That's right. Yeah. So to answer Shiraz's question, when we're working for 5D polytopes, we worked with vertices of all y between -15 and 16. So these are 5-bit numbers we're using here. Then we have 6 vertices. So the total space with 6 vertices in 5D. So it's 5 times 6 times 5 for 5 bits for each point. So total space has got 10 to the 45 states in it. By sampling some fraction of 10 to the -35 of these states, so 10 to the 10 states we sampled over 600,000 iterations of the genetic algorithm, we're able to find that we found this many reflexive polytopes. Once we apply this equivalence by GLN and permutation, this comes down to about 10 to the 5 polytopes.
And the rate of finding decreases as you increase the number of runs.
Yes.
That's you know what shape that is? How is it approaching? Is it saturating?
It's still increasing, but it's slowly increasing. So it's getting close to saturating.
And do you have a guess for an analytic form of that?
I haven't thought about it. I don't know. But typically what's nice about this kind of algorithms is by only visiting a fraction of the space, a very tiny fraction of the space available in the state space, you're able to find lots of solutions. And this again sort of mimics evolution in the sense that by sampling small parts, you get fit individuals or whatever milieu you're in.
So now if you start, so if you started with another population, once again you would get a lot. Is there big commonality in the things you get, or are they completely different?
They're often, I don't know, I haven't looked.
I was wondering, would it, if you want to generate lots, is it more efficient to keep running one population, at some point stop, generate a new population, and start again? Because it seems at the beginning you're doing really well.
Yeah.
So it feels like you should just,
maybe.
after points.
This is logarithmic though, right? This is,
Yeah.
Yes.
Sorry, I didn't understand like why exactly selection and loss of was necessary to get the impact for. Then why only not mutations can?
It turns out that when you run these things, both features are necessary for it to work well. You do this in lots of experiments, for example, using genetic algorithms. And typically, if you turn one of these things off, you're not doing so well. You need both. You want to incorporate, if you have things which are good, relatively good at fitness, and if you incorporate the best aspects of this, the best aspects of that, that enables you to find things which is even better. So hopefully what parenting is like. I don't know. But this is the philosophy here.
Is there a sense in which like small changes here don't change D rapidly or something like that?
I don't know. I haven't looked.
Because otherwise you might totally mess it up by doing this.
I don't know.
How would three-body treating?
Again, it's a good thing to try. I don't know. People typically just do pairwise. I don't know. You can do things more complicated.
What's the selection condition? What is the selection condition you're putting?
How close it is to being reflexive? There's a score you assign based on this. It's a formula.
So you just start with a population, and that population will turn into a new population with better fitness, better fitness. And this graph is telling me that.
This graph is telling me how many reflexive polytopes I'm finding.
The perfect things.
The perfect things.
And how many, what is the population? 10 to the.
The population was maybe like 1 million. Start off.
Million, but you're getting more.
Well, I mean, as things become perfect, you replace them, right?
Oh, you replace them.
How sensitive is the graph to the mutation rate?
We ran this one once up to the spinning epochs. I don't really know how sensitive these things are.
Is it related to like if you do it like if you take mutation rate very small, it will reach this flatten out very late. But is it expected?
If you mutate once, that's typically bad because it's offsetting the selection bin. You're essentially randomizing things. You mutate once. Typically, want your mutation rate to be relatively small. But you want it to be non-zero.
Yes. So your this thing the place where it's saturated starts to saturate. It should depend on.
It may. I haven't really checked. By playing these parameters. It's like simulating an alien in a sense. You want to have some bad choices you make along the way in order to get out of a relative minimum or to explore more of the space, but the state space. Mutation enables you to do that.
Is there something you can say generation by generation? Change? Generational change?
I haven't looked, I don't know. Presumably you can take these snapshots at different epochs and see how well you're doing at a population level by looking at the individual elements. I haven't looked.
There is a generational, will be any generational change.
There could be, yeah.
This is really cool because it's so simple.
Yeah. Okay, so these are examples of new 5D reflexive polytopes of Calabi-Yau manifolds. So these are the vertices. You can just plot this and verify this is the right answer. You can check that the distances are as predicted, and there's a single interior point and all that. So you verify, and once it gives you an answer, this is indeed reflexive. And so we found a bunch of these new examples that people hadn't found before in previous searches because they don't correspond to these maximum polytopes. And based on what we've looked at, we conjecture that there are exactly 15 reflexive polytopes at H11 equals 1. We haven't been able to find any more. As H11 is small, we're typically close to the origin. As H11 becomes larger, points start moving away from the origin. So by looking at a box of reasonable size, we found 15. We think there are only 15. H1 equals 1.
So what is that from the data, the polytope
You
data?
can calculate that in the polytope.
Simple formula.
Yeah. And then,
Sorry,
yeah.
is this an observation that if H11 is small, it has to be closer to the origin, or still
it's an observation.
expected?
The experts weren't surprised. It's an observation that seemed reasonable to toric geometers and so on. It turns out that if you take M theory, and you compactify this on a fourfold, which you build out of one of these 5D polytopes, in order to get n equals 1 in 3 dimensions, the Euler characteristic needs to be divisible by 24, 224, and 54 or something like that. This 50 is a typo. But so we found polytopes that have these certain divisibility properties. The second polytope I showed you, the other character has the divisibility properties that I want, and is then a new way to engineer n equals 1 theories in 3 dimensions based on this Calabi-Yau fourfold. So you can do selected targeting of kinds of polytopes you like for phenomenological reasons.
Can add that to fitness.
Yes.
N equals 1 means 2 supercharges or 4 supercharges?
N equals 1 means 3D means 2 supercharges. Okay,
Also go from polytopes to Galilean manifold.
this is what we're getting to next. So in order to do this explicitly, what you can do is you triangulate the simplices of the polytope. So the triangulations you want in order to get a Calabi-Yau are called FRST triangulations, or fine regular star triangulations. So a triangulation means the simplices are such that the intersections of any 2 simplices gives you a face, and the union of all the simplices recovers the entire polytope. The fine part says a triangulation uses all the points in your point configuration. The regular part is something about getting these things from a projection, and the star part is the origins of vertex of each of the simplices. So you look for these triangulations with certain properties, and we did this by brute force for all Calabi-Yau threefolds. H11 must equal to 6, and we tabulated this in a database back in 2014. We revisited this problem using machine learning. We found that we could do the same thing very, very quickly, and we could similarly triangulate larger and larger polytopes we couldn't triangulate before in an efficient sort of way. So how do you do this? What you do is, so any 2 FRSTs of a polytope with the same 2 faces are topologically equivalent. So let me just give you an example. You take a cube, you look at the faces of this polytope, and then you find that all these faces are essentially squares. And you triangulate these squares. And then you put these together in a sort of way. So that's how you do these triangulations. You piece together these things consistently by choosing some fitness function. It turned out that we could use this. We tried using genetic algorithms this problem again, and we didn't get it to work very well in genetic algorithms. So we used reinforcement learning. We got it to work using reinforcement learning, which is another machine learning setup. These other guys, they managed to get genetic algorithms to work on this problem, where we didn't. So again, it was a bit of finesse and a bit of luck involved in how you set things up in order for your particular machine learning tool either work or not work on a particular problem. So we were able to triangulate these geometries and get explicit Calabi-Yau constructions. So a question you can then ask is how many Calabi-Yaus are there? This is a question that is not answered in literature. So when do you know 2 Calabi-Yaus are the same? There's a theorem for that for threefolds. It's called Wall's theorem. First, the Hodge numbers, H11 and H21, need to agree. Second, the second Chern class needs to agree between these two different manifolds. And third, the triple intersection numbers of the 2 cycles and 4 cycles in your geometry, they need to agree in the 2 cases. But they agree only up to GLH11 rotations, because these indices on the second Chern class and the triple intersection number, they run from 1 to H11. So if you do a GLH11Z transformation of this to this with some matrix, then these 2 Calabi-Yaus are the same in a different set of bases. So that's a statement of Wall's theorem. Yes. So there are certain properties these triple intersection numbers, for example, need to satisfy. The GCD of DIJK and D tilde IJK need to be the same. So Hoops in 1991 classified a number of these conditions on when these 2 Calabi-Yaus satisfy Wall's theorem. But this list is not a complete list. So it turns out that different triangulations of the same reflexive polytope can give different Calabi-Yaus. And you also get the same Calabi-Yau starting triangulations of different polytopes. So there's no known total number of Calabi-Yaus. So we try to use machine learning to learn this equivalence that's embedded in Wall's theorem. And different people have tried various things. There's still no complete answer to this question.
But you're trying it 4 of these Calabi-Yaus you get from reflexive polytopes.
Yes.
Which are not the most general present.
There are probably more general constructions available, but so far the biggest data sets we have are from these reflexive polytopes. And we know no similar statement for fourfolds. The naive guess is in addition to this stuff here is a quadruple intersection number instead of a triple intersection number for fourfolds. There's also a 3rd Chern class for fourfolds. And if those 2 agree, that's a naive guess for what Wall's theorem will be like in 4 dimensions, but that has not been proved. Okay, so we don't know how many Calabi-Yaus there are. It's conjecture the number of Calabi-Yaus is finite, but we don't know. Okay, so that's the topology part.
Is that a question of great interest to mathematicians?
Yes.
So what would be different if these data match? What would be different? That would definitively let you say that Calabi-Yau are different. Because for a given class, there is unique metric, right? That is the theorem. So,
right.
So what is different?
I guess certain topological invariants, like you can
Which are not
Donaldson-Thomas invariants, Marmotha invariants, things like that, and see whether they match.
I see. Maybe elliptic genus.
Yeah.
As opposed to just this one classes.
Okay, so that concludes topology. You move on to geometry and discuss how to approximate Ricci-flat metrics on Calabi-Yaus. So one thing to do is to solve the Mongeron-Pair system directly to get a flat metric out of that. This is an approach that Hedrick and Wiseman applied in the early 2000s or mid 2000s, and they were able to approximate Ricci-flat metrics on certain Calabi-Yaus this way. Subsequent to their initial paper, Donaldson had a paper that gives you an iterative procedure to get to the Ricci-flat Calabi-Yau metric. So it goes through a process of constructing balanced metrics at different levels K. These levels correspond to the degrees of homogeneous polynomials you can write based on the coordinates you have for your Calabi-Yau in an embedding space via Kodaira embedding. It turns out that this is proved to converge. The convergence is rather slow. So for example, for the quintic, the number of homogeneous polynomials grows like k to the 4th at each level k in the variables you have quintic. And this polynomial growth in the number of parameters you need to worry about, Donaldson's algorithm, means it's very difficult in numerical to get good convergence. Provides a baseline for comparison. What we found what 3 different groups found sort of independently in 2020 during the COVID year was that neural networks can approximate Calabi-Yau metrics. and I'll tell you about our approach to this problem. So the neural network approximation the neural networks we discussed previously for learning Hodge numbers, we knew the answer. So we're training on an answer that we knew. We're using mean squared error in order to lower the difference between prediction and the actual answer. Here we don't know the Ricci-flat metric. We only know properties of the Ricci-flat metric. So we write down a loss function that captures those properties. And we try to see whether we can minimize that loss. So for example, one of the conditions we want is Ricci flatness. So you can take the components of the Ricci tensor, take their absolute value, and have that sum be the loss function. So that if you evaluate this at a bunch of different points, you get that sum to be everywhere, and you have a Ricci flat metric. The difficulty is that in order to compute the Ricci tensor, take further derivatives. So the derivatives tend to amplify the error. So you want to avoid taking derivatives where you can. So the thing that we decided to do, in fact, all these different groups found, was that the way to do this is to write down the volume in two different ways. One way is metric dependent, one way is metric independent, and just subtract the two. You take the absolute value of those two different calculations of the volume and use that as your loss function. So one way to calculate the volume of Calabi-Yau is to take the top holomorphic form and wedge up the top anti-holomorphic form, integrate that over the manifold. That gives you the volume. Another way to do this is to take the Kähler form, which is a 1-1 form, and then wedge it together twice. So you have J, wet J, wet J, and you integrate that over the manifold. That is also the volume. And
so sorry, the last one was obviously the volume because it was like coming from the metric.
Yeah.
And why was the first one the volume? Remedial.
The volume is in these cases is topological. So it's just this is a topological way of calculating the volume.
Right.
So the metric dependent way, you start with the Kähler form. The Kähler form you obtain from the flat metric. And the Kähler form has certain properties, it's closed, and it wedges with omega to get 0. So these are the conditions. And you just take your loss function to be volume 1 minus volume 2 absolute value.
So what are you doing with the moduli? Are you fixing the moduli?
I'm fixing the moduli. I'm choosing a Kähler class. So other conditions, if you're working in a coordinate patch set up on a manifold, you want to make sure that the Jacobian takes you from the flat metric on one patch to the flat metric on a different patch. You might include compatibility conditions from coordinate patches. May have multiple Kähler classes. You want to ensure, say, the same Kähler class. You basically impose all of these into the loss function and just find a solution to this. In the particular Calabi-Yau case, it turns out there's an easier way to do this. There's a global function phi that relates the pullback of the 3D metric from the ambient space to the manifold. If you can find this phi, you can take the initial seed metric to the Calabi-Yau metric that you want. So our neural network is being trained to learn this phi in order to match these volumes.
This is just a mathematical result that
Yes.
given to the metric plus one. So
Yes. This isn't Green Schwartz and Wynn.
This is what?
This isn't Green Schwartz and Wynn volume 2. This formula here. Okay, so this idea of using a loss function, which is essentially left-hand side minus right-hand side absolute value, now goes by a name. It's a physics-informed neural network. It's used to solve, solutions to differential equations, for example. So in principle, if you want to find new solutions to Einstein gravity, you can take G mu nu minus T mu nu absolute value as your loss function and just find a solution.
I think the previous transparency. So if we did actual world sheet RG flow, so Ricci flow, is the right hand side for such metrics of the form the bar of something?
Yes. I'll show you something about Ricci flow momentarily, but yes.
So then that's the proof, right? Yeah.
So we can use these kind of technologies, for example, to do other things. This is not my work. This is work that Fabio Bula and students are doing. They calculate SLAG, special Lagrangian submanifolds, in Calabi-Yau using these similar ideas. So here you want the Kähler form pulled back on the submanifold to be 0, and you want the homomorphic form have constant phase. These are the Lagrangian special conditions. In case of the quintic, RP3 is a special Lagrangian submanifold. It's known mathematically. And in a particular limit, the T3 fiber is a special Lagrangian submanifold. But they're looking for other ones using these methods.
And phi is the Taylor potential then if I do Gij dot, I would get Rij.
Yes.
And Rij is del bar of the Taylor potential. Is that right?
G is del bar of the Taylor potential.
G is del bar. And so R is
something
more complex.
D bar of log det G.
Okay, great. So that phi is that, yeah. Great.
Okay, so you can look for more complicated things. If you want, for example, to wrap D branes on cycles on a Calabi-Yau, you'd look for special Lagrangian submanifolds in order to wrap D branes. Okay, so Ricci flow, which Shiraz mentioned, this is for Dan back in the day. Notice Ricci flow is like RG evolution of a nonlinear signal model in the string world sheet with some specified target space metric. So this idea is floating around in the string literature. And in fact, in Perlman's first paper, he makes some comment about string world sheet versus string spacetime geometry. Sort of a throwaway comment he puts in there, but it's there. The idea behind Ricci flow is that you can use a technique to say that changes in your metric are proportional to the Ricci tensor, and fixed points of this flow are obtained when the right-hand side vanishes. So you can look for a Ricci-flat metric in this way. Perlman's observation was you can convert the usual Ricci flow with surgery equation into a gradient expression by essentially introducing a dilettante. Then you have a flow equation for the metric, a flow equation for your dilettante that you introduce. And the dilettante equation is just a backward E equation. So you can look for a simultaneous solution to the system of equations in order to find a metric which flows from your seed metric to the Ricci-flat metric. It's a fixed point of the flow.
Was the metric, gradient flow with a metric of the space of
yes.
things? Was that a positive definite metric?
Yes, I think so. So we can try to start with the pullback for PDC metric to solve the flow equations. We were able to do this for the torus, but we weren't able to do this for K3 or Calabi-Yau threefolds. But for the torus, we just take a bunch of points, and you start out with the Fibonacci 2D metric, and you flow this to, you apply Ricci flow, you're able to get the flat metrics out of this.
Just to say, when a paper we wrote 20 years ago, we wrote down these Ricci flow equations as gradient flow.
Yeah.
But the metric on the space of metrics was, metric and dilettante was not positive definite. The dilettante part was non-positive. We thought it was of limited use. Maybe it was. Yeah. We certainly
This is the sign of
sort of probably related. Certainly, I thought there was a problem. Again, we needed to put the dilettante. Okay, thank you. Yeah.
Okay, so let me do this for a Calabi-Yau now. So the one thing I need to tell you about is point selection. How do I choose points in my Calabi-Yau to train with? So the way that people have come up for doing this, the best way people have is the algorithm that Shipman and Zeldridge came up with. The idea is to think, for example, the quintic as being embedded in P4. We know the metric on P4, standard Fibonacci 2D metric, and we choose points with respect to the Fibonacci 2D metric in P4. We draw lines through pairs of points and see where intersects our hypersurface, and those are the points we take. So if you take, for example, the quintic, this is some point selection, and here's a heat map of the points in some coordinates I picked. And then if I take the dwarf quintic, where I include this extra term, which is also the quintic polynomial, I get a different point selection. So the point selection is then sensitive to the actual complex structure parameters of your geometry. So we just choose points this way. And then we use a spectral network. So it's a neural network where we massage these terms so that the actual input isn't the metric itself. The initial stuff we're doing, we're learning the line elements. We're feeding it some seed line element and using this to train for phi or whatever else in order to get the flat metric. Here, we're feeding it this matrix of how the points look in the ambient space. And we feed it these points in real and imaginary parts. We feed this to a neural network, and we predict phi. And this phi is chosen so that we take the seed metric, we manipulate this in the Calabi-Yau, which is flat metric.
And the error function is this difference between the volumes.
Yes.
How do you compute the volumes from these points?
We predict phi, we calculate this g, and we keep the volume of g. We're just using this as the input.
So coming back to the gradient, my memory is that our gradient function was the space-time action. Is that same thing here? Yeah, right.
Here, yeah, basically.
Space-time action. Yeah, good.
Okay, so this is our spectral network. It turns out the spectral network works better than feeding it the line element. This is a comparison between the two.
So what do you mean spectral network?
We call this a spectral network. This is our network that we use. We're feeding it these as the input.
So this is a neural network, right?
This is a neural network. Okay, so let me look at K3 to start. So I'm looking at a particular description of K3 as a quartic equation in projective space in 3 dimensions. It's singular for particular values of lambda. 3/4, 1, 3/2, and 3 with singular values. And this number of singularities changes based on what lambda is. So you can have 8, 16, 12, or 4 singularities. The x1, lambda equals 1, that singularity is a T4 mod Z2 Calabi-Yau, K3 Calabi-Yau that Kashfu and collaborators looked at. So if lambda equals 0, we just have the pure quartic, we find that our neural network is an order of magnitude better than the previous neural networks that were used to find Ricci-flat metrics. And it corresponds to about the 8th iteration of this Donaldson algorithm.
So what was the blue line? What sort of input do they have?
There, the blue line corresponds to inputting your best metric that you have currently at each stage as a line element. Or permission matrix as flat. So you can ask how well you're doing. And just like we're using the volume in 2 different ways, a topological way and a non-topological way, you can compute topological quantities in a geometric way. So you take the Euler character, you compute this by integrating the Euler density, which is a function of the Riemann tensor. So you take a geometric quantity to compute this topological quantity, and you ask how close you are to your known value. And this is another way of assessing how well you're doing. Because we're working Kähler manifolds, it turns out calculating these quantities isn't so bad, because a lot of the Christoffel connection elements and the Riemann tensor elements just vanish due to Kählerity. Okay, so this is lambda equals 1. The expected answer is 24. We find that away from lambda equals 1 exactly, where we don't do so well with the numerics, we get 24 on the nose for the Euler character. And these are the other singular values we look at. Close to the singularity, so lambda equals 0.98, 0.99, 1, 1.01, 1.02, we're still doing better than the alternative ways of calculating these things, but you see that the errors are certainly getting worse close to the singular point. The formula for the Euler character is basically integral Euler density plus twice the number of singularities. Reason is, the singularities we have, they're of A1 type. So you blow up an A1 singularity or replace it with a P1 or an S2. The S2 has a genus of 2. So twice the number of singularities plus the integral of the Euler density over the rest of the manifold should give you the Euler character, which is 24 for K3. And it does. Okay, so going from 2 dimensions to 3 dimensions, we'll work with real Calabi-Yau manifolds and calculate things here. So as I said, in order to do particle physics in the string construction, we need to think about this vector bundle on top of the Calabi-Yau. So the vector bundles we'll choose are holomorphic vector bundles, meaning they've got holomorphic transition functions, and there's some technical conditions called mu stability, the connection solving the Hermitian-Yang-Mills equations, but we can implement these other conditions as well. The low energy matter spectrum, so I'm just reviewing Green, Schwartz, and Witten here. The low energy matter spectrum will specialize in the case of E6. This is the simplest case. The reason is that SU3 holonomy is associated to the Calabi-Yau by definition. The commutant of SU3 in E8 is E6, so the gut group that gets left behind is an E6 gut. In this E6 gut, there are going to be 1-1 forms and 2-1 forms. These correspond to generations and anti-generations in your spectrum. For the 1-1 forms, the Yukawa couplings turn out to be topological. So you don't need to know the metric to calculate the so-called 27 bar cubed Yukawa couplings. The 27 cubed Yukawa couplings, however, are non-topological. You need to know the metric in order to calculate these guys. This unnormalized Yukawa coupling calculate, which is dependent on the cohomology class, but not on the actual representative. But in order to calculate the normalization of these Yukawa couplings, you need the metric. Okay, so that's where the metric enters in the story. Calculate these particular 27 cubed couplings. So the normalized Yukawa couplings are obtained by essentially canonically normalizing the term of the Kähler potential. There's this Hodge star operator appears. This Hodge star operator invokes the metric. The normalization, then you take the unnormalized ones and you normalize by diagonalizing, since we're talking about basis, and you divide out volume, you get these physical Yukawa couplings. Those are the actual numbers that appear in the Lagrangian effective theory.
So just can I make sure I understood? So you say that in some normalization, all the Yukawa couplings are topological and computable or not?
For the 1-1 forms, these correspond to low energy theory, the 27 Borg cubed interactions, the E6. These guys are topological.
Okay.
The 2-1 forms, which were also there, their Yukawa couplings correspond to 27 cubed couplings, the E6. These ones are not topological. These ones you need to geometry.
It's just genuinely.
Yeah.
It's not even a normalization.
Yes. So so in order to start with the unnormalized couplings and make them normalized to get the physical couplings, you need to know the rest.
Yeah, you need the kinetic.
Yeah. So in the standard embedding, the normalization turns out to be independent of the Ricci-flat method. And we use this standard embedding in order to check how well our machine learning is doing, and we'll move away from non-standard embedding afterwards. Okay, so what's the standard embedding? Standard embedding is saying the holomorphic vector bundle, which sits on top of your Calabi-Yau, is just a tangent bundle. So because the tangent bundle is determined by the manifold itself in a very simple way, the metric on the manifold is doing double duty as a metric on the fiber. So the deformations of this tangent bundle, these correspond to the complex structure moduli of your geometry. And the number of generations in the setup is given by the index of the Dirac operator, which is 1/2 the Euler characters to value, which is given by the Hodge numbers we have for our geometry. So we can calculate in the standard embedding the Yukawa couplings in 3 different ways. We can use Von-Pearson geometry by computing period intervals using our Spencer map. We can also compute explicit harmonic forms using our Ricci-flat metric. Compare the 3 different ways of calculating these things. So because we're working in the standard embedding, and things depend on complex structure moduli and not Kähler moduli, in every Kähler class, get the same answer as the Yukawa couplings. That's another benefit of the standard embedding. This means standard embedding is very, very special. It's not a generic case. Okay, so you do some period intervals. Candelas, Osa, Green, and Parks essentially told us how to do this. You solve the Picard-Fuchs system. Picard-Fuchs system is particularly easy when H11 is when H21 is a few. When H21 is equal to 1 is a system of ODEs. When H21 is a 2 or 3, PDEs you can actually solve. But it becomes very, very impractical for H21, which is bigger than 2 or 3. But you obtain from this the Von-Pearson metric on the complex structure moduli space.
So sorry. Vishnu.
Yeah.
So in the case of the Yukawa couplings that are not topological,
Yes.
then they are holomorphic functions of the complex structure moduli.
Yes.
And that holomorphicity doesn't allow you to just somehow using that to compute it analytically.
Yeah.
No.
Okay. So You can also do some complicated algebraic geometry, which I won't go through the details of here. Called a Dyer-Spencer map. It also lets you calculate Yukawa couplings and standard embedding without knowing the Ricci-flat metric. You essentially use some algebraic geometry tricks in order to do this calculation. I'll go through this with you privately if you want, but we not do this in the interest of time. There's a different way of doing the same calculation. It also leads you to the Witwatersrand metric. The Witwatersrand metric turns out to enable us to do the normalizations properly in order to calculate the physical couplings. The third thing to do is to use harmonic forms. So in order to write harmonic forms, you just look at the Laplacian acting on some sections of your bundles you have in the story.
So yes, just going back to that, the space of holomorphic functions, isn't that some finite dimensional space?
Sure.
And so your ignorance is up to some finite numbers, right?
You want the finite numbers to
I understand. Yes. So, but you could parameterize your ignorance and then in terms of some finite numbers. That's better than parameterizing in terms of functions.
No, these are continuous functions. These are continuous space in the moduli, right? So
yes.
Yeah.
So I was thinking that is the space of holomorphic functions
yes
on a Calabi-Yau, is that finite dimension? It's generally hard to make holomorphic functions on a compact manifold.
It's countable. I'm not sure it's finite.
Maybe not finite. Okay.
Okay, so we can calculate harmonic forms explicitly and use these harmonic forms in order to write down these normalizations. So in knowing what the Laplacian is here, we also need to know the metric. So this is where the metric enters. The metric really enters two places, either in this dot square operator or in the Hodge star operator. Both of these things need to know the metric. That's where this becomes a geometric problem rather than a topological problem.
I see. Sorry, a counterexample what I was saying was in like CP1.
Yeah.
All the representations are holomorphic. Yeah, so all arbitrary degree polynomials. Thank you.
So yeah, so I mean countable but not.
Yeah.
So you can use a neural network in order to find these harmonic forms. Second neural network based on the neural network you already have for the metric. And these methods apply to any value of H21, not just H21 being small. So again, the metric is associated with two different things. When you're using the Hodge star operator, you're using the metric in order to raise lower indices. And when you're using the Laplacian, you're using the metric to define the Laplacian. So in order to write harmonic forms or to apply the Hodge star operator, you need the metric. This is where the formulae that I've written, it seems very messy here, but the metric is in fact in all of these stories. So we just show you some results. This is the quintic. So I'm looking at the quintic with particular value of, I guess, psi equals 0 is what I'm looking at here. And this coloration is basically the strength of phi. So the things which are brighter colors are larger values of phi. And this enables us to go with the 3D metric pullback to the Ricci-flat metric by using this phi on different points in this Calabi-Yau. So if you look at the periodic calculation, the Dyer-Spencer calculation, to essentially line on top of each other, even near the singular point. And if I look at doing a calculation using the harmonic representatives, in this particular case, the answer is some for period intervals is some ratio of gamma functions, and the machine learning calculation and the calculation analytic is agreed to 3 decimal places. So the machine learning is learning the right value here for Ricci-flat metric and also the coupling based on this. So if you look at a particular quotient of the quintic, you mod this by Z5 times Z5. This is a model Jissler and Green looked at back in the day. They were able to normalize Yukawa couplings. We were able to do the same thing, and our machine learned things are essentially on the dot as far as the analytic results.
They have analytic results.
For this particular value, they're able to do period intervals, standard embedding, and analytic results. So if you look at the quadric, another Calabi-Yau in P3 cross P1, here's a description of this geometry with some parameter psi, which is a complex vector parameter. This has got two Kähler classes. So I'm looking at the Ricci-flat metric, these two different Kähler classes, and I find I have two different answers basically. So I get two different Ricci-flat metrics as expected. I'm plotting here the Crutchman scalar. So I construct a scalar out of the Riemann tensor, and I notice doing a histogram of what the scalar looks like, and with Ricci-flat metric in these two different Kähler classes, I get a different histogram than I did with the Fibonacci metric I started out with. So machine learning is changing this distribution into this distribution, and it's different for the two different Kähler classes. So there's actually some learning happening, and there's some things that you can look at by using other invariants.
What is the x-axis?
The x-axis is this parameter psi. Sorry, psi is psi is fixed. This x-axis is
Points?
points, I guess. It's a histogram of what the spectrum scalar looks at various points.
Oh, histogram. It's histogram.
Yeah, it's histogram. Yeah, and then you can look at different descriptions. The different Kähler, the two Kähler classes, we find different descriptions have the same profile as well. So we're actually learning things the same way, irrespective of how we characterize the Kähler classes.
So is it clear? Is it automatic from your? I haven't followed.
Yeah.
Is it automatic from your method that your Yukawa couplings will be holomorphic functions of the moduli?
Yes, that's my construction. Yeah. So
This is interesting. So this Greshwood scalar, is there a particular distribution it has on the Calabi-Yau? From this side?
no, it's not known. I mean, it's
Seems to have that shape.
it has this shape that it would have. I mean, all things look like a bump that goes down again, right? So maybe it's just a single bump, and I think that's the only feature you extract out of this, maybe. But I don't know of any people who've studied this in the past, and there hasn't been anything systematic that I'm aware of. Okay, so this is the Euler density. We also see histograms for Euler density of these different Kähler classes. They're different as a function of psi now, the complex vector parameter. So we're able to characterize these different geometries, and then with the intersection of two cubics, and I find that the different ways of calculating these things agree on these on this Calabi-Yau as well. And here I'm calculating this dashed line is the period interval, and then the points are different ways of calculating using, for example, the Gauss-Spencer map, using these harmonic representatives. These harmonic representatives, the Gauss-Spencer map, they all lie on the curve. And if I look at other things, non-harmonic representatives or things that are non-global, they lie further away from the curve. So I'm able to calculate these things in the places where I know the answer based on these other methods. Using machine learning, Ricci-flat metric, ability to calculate these things, they agree. So this is the actual Yukawa coupling. The previous thing was the metric. Then I'm looking at the Tian-Yau quotient. This is one of the first Calabi-Yau manifolds people used for standard model building. If you take a particular quotient of this, you make this chi equals minus 18, chi equals minus 6. The absolute value minus 6 is 3. It's a 3-generation model that people like Green, Kirkland, Meyer, and Ross used to construct initial standard model-like theories. We're looking at a Calora-Mahapatra construction based on this. And here we have these unnormalized Yukawa couplings that we calculate, and they agree with the ones in literature, modular errors in literature. And then normalization based on calculating the Ricci-flat metric shifts these points we go from the red to the black dots. That's what normalization is doing, shifting the couplings that appear in the physical Lagrange. In this particular case, if we look at how these ratios, these couplings look like, we find that certain ratios are essentially the same, certain ratios change quite a bit. If we look at the actual values of the couplings, we see from going from this epsilon equals 0 point, which is a symmetric point, to epsilon equals 2, which is a non-symmetric point, we see hierarchies that are exponential appearing in these Yukawa couplings. So this may be some mechanism that explains why we have one light generation, one middle generation, one heavy generation of quarks in our theory. These are the quark Yukawa couplings we're looking at. So this is the light generation, medium generation, heavy generation. So we're seeing the kinds of ratio, the hierarchies we see in the standard model already this n equals 1 theory in the Yukawa models.
And so, but epsilon is this complex structure, right?
Yes. Yeah. This is not moduli stabilized, so it doesn't mean anything by itself. You need to find some moduli stabilization mechanism at a point where these hierarchies exist. Would this be meaningful statement about physics?
Then what would be the x-axis?
Sorry.
No, but just that point.
Yeah, it's just this point. I can add other deformations as well and just make it more complicated. But
Yeah.
we would like to find these hierarchies at a stabilized point. But the fact these hierarchies exist is already exciting to me. That without doing much work, we go from 0 to 2 by turning one number here. We get these hierarchies. Okay, and we see these hierarchies have interesting things happen at singular points, these geometries. Go into that detail if you want. But we just advertise our code base. The other code bases people have come up with. You use the QR code. But this is the code actually working. This is sped up by a factor of 20 the slide, but it's not a huge speed up. I'm looking at the quintic, and I'm turning on this work parameter psi, and I'm using the metric that I've calculated to calculate the Euler characteristic by integrating the Euler density. Get minus 2.001701. The answer should be minus 2. So getting the right answer based on this Ricci-flat map. Okay, so what are we going to do next? We've done the standard embedding. We're going to look at non-standard embeddings. We can think about the standard embedding itself as a non-standard embedding. And this is what this mess of algebraic geometry ends up doing. We try to calculate these things in the generic setup. The generic setup would be a non-abelian vector bundle on top of the Calabi-Yau. And this is the kind of instructions that these million standard models I talked about used. So far, none of those calculations, none of those geometries, anyone's done a calculation of the actual Yukawa couplings there. That's what you'd like to maybe look at next. So we're developing technology to do this. Better point selection scheme may help. So this is related to something called Bertrand's paradox of statistics. How do you choose a random chord on a circle? One thing to do is just 2 random points of the circumference and just draw a chord between them. Another thing to do is choose a random radius, pick a random point on the radius and draw them perpendicular. Third thing to do is just choose a random point in the disk, not having the midpoint of the chord. So these 3 different selection schemes give you 3 different distributions of random chords. And Bertrand asked, what's the probability that a random chord is longer than the length of the side of the equilateral triangle that's inscribed inside the circle? And these selection schemes give you different answers, 1/3, 1/2, and 1/4. So your answers are sensitive to how you choose points, basically. So in the case of T2, where we know the analytic answer, suppose we choose points uniformly with respect to the flat metric. And suppose we compare this to the point selection scheme we've been using in the ambient space. It turns out that choosing points with respect to the flat metric gives us a different distribution of points than choosing points with respect to the ambient space. And this selection of points converges much, much faster than this set of points. So a better point selection scheme may give us a better approximation to the Ricci-flat metric. And we're playing with finding
so dynamical.
Yeah.
Yeah, do it, then change it.
Yeah. So we're also looking at towards analytics and certain limits. This is a comparison of various different numerical schemes people have looked at in the literature. And we can compare these things to, we take one of these things and come up with symbolic formulae. So Mirianic and Mishra and Leo Lukas did this, and they found symbolic formulae that approximate the kinds of errors we get from a neural network. There may be some nice formulae for the Ricci-flat metric on quintics, for example, that we can explore. Another thing to do is look at the large complex structure limit. The large complex structure limit, there's this SYZ conjecture, Strominger-Yau-Zaslow, that says that in this limit, the Calabi-Yau should look like a torus fibered over a base. So you can look for coordinates that make the torus vibration explicit in the large complex structural limit, and then maybe work backwards towards analytic results. And then we can go after some first principles top-down derivation of realistic standard model string theory. and to which we should add selection of vacuum gives us a synergy geometry as well in type 2. And in order to figure out where to put anti-branes and fluxes, it's useful to have a characterization of curvature on Calabi-Yau. So find Calabi-Yau stratigraphic threads, for example, for these purposes. Then you may look for regions of high Frenchman curvature in order to find these threads. So that's something you look for in KKLT or Lorentz scenarios where to construct series space. So it's too bad to leave this here. Don't worry about that. Anyway, thank you.
Any other questions?
Are the polytopes in D-dimension related to polytopes in D+1 dimension?
You can sort of build trivial polytopes in D+1 dimensions, starting out with polytopes in D dimensions. So, for example, if I had the square, one of my polytopes in 2 dimensions, if I had a point 1 above and 1 below, that would be a reflexive polytope in 3 dimensions. So you can always do that trick in order to build a new polytope this way in 1 higher dimension. Most polytopes in the higher dimensions are unrelated to the polytopes in lower dimensions.
Most polytopes are not related.
Yeah.
So you can't use the data of D-1 dimension.
No.
Is it completely impossible that there exist, let's say in K3 manifolds, that there exists a nice analytic form for the metric that we haven't found?
Well, I mean, Shemet and company will tell you that they have found one on this Kummer surface.
Good.
But I would say that it's not a very nice metric in the same way DZ was a nice metric. The torus. It's a much more complicated thing they found. But in principle, they found something.
But
that's very valid for that special point. Yes.
Yeah. So now suppose we moved away from that. Is there some hope that we could, move towards finding analytic metrics everywhere?
That's my hope, yes. I don't think this is impossible, at least on very symmetric Calabi-Yaus. I think if you turn on a bunch of complex structure parameters, it becomes much more messy. But if you take, say, the quintic, the Fermat quintic, or the things like that, I'm hopeful that there are analytic expressions for the metric there.
And are you hoping that your results will help you?
I'm hoping that if you can say, for example, what things look like in this large psi limit, you can work backwards. So I can find, for example, a torus vibration.
Right.
I'm not expecting that the flat metric on the torus is times the flat metric on the base is the answer. It's probably some combination of curvature on the fiber canceling curvature on the base in order to get the flat metric. But if I can do that, I can then sort of work backwards. Maybe I can take that analytics from the extreme end and move it towards the interior.
I have a question. So is it possible that since there is no necessary symmetry at the usual energy scale, so that the Calabi-Yaus are considered because you want something is equal to 1?
Yes.
So is it like maybe heterotic is compactified using some generic, maybe not Ricci-flat thing, and that gives standard model? Or is there a way to say that shouldn't be?
That can certainly happen. So people, sometimes say there are ways to get an equal 0 theory starting from a string compactification. They're absolutely correct. There are ways to do this. You don't need to go through supersymmetry. But we don't have control the same way we do with supersymmetry. Moreover, I think there are good phenomenological reasons for saying supersymmetry is there at some energy scale. For example, a hierarchy problem at the weak scale and the Planck scale is sort of solved in a nice way by supersymmetry, even if it's broken supersymmetry, whereas you don't have that kind of thing. We have proton decay being suppressed in SUSY theories in a natural sort of way with those R parity. But those physical considerations also motivate these constructions.
And just to add to that, I mean, at least independent of phenomenology, these constructions are very clean because they're correct within string theory. But if you try to do what you're saying and turn the coupling constant down to be non-tiny, then at one loop there'll be a cosmological constant. And that will bend space away from flat. At 2 loops there'll be a cosmological constant. You want the coupling to be 0.1, it's way out of control. So, I mean, that you're going to have this problem anyway once you break supersymmetry here. But at least you can postpone. Like, I mean, it seems to me just to say that this is the elephant in the room with string phenomenology. That if we want to get a model with coupling 0.1, sorry, in the real world, and we know that supersymmetry is only broken, that there is supersymmetry, if at all, only after 1D, then I don't think we have any model which has this general feature. And you can do calculations, which then has a space that is big compared well. So I think
experiments already force you to fine tuning, even without, thinking about anything else.
But let's say I don't mind fine tuning. Let's say that is in the mind of the physicist. That I don't mind. But what I want is a model where I can do a calculation. However you got it. So it seems to me, please correct me if I'm wrong, but it seems to me if God comes and hands us one of the flux compactifications of Musso and Polchinski, tells us that's the model in which you live, and you were skeptical of divine word, you would never be able to verify it. Because you'd need to go to, 20th loop order, just to check whether you've got a big space, right? Because the fine-tuning in your bare Lagrangian, you'd have a very highly curved space. And then the cosmologic, the loops will cancel it. And just to check that, so before you can do any phenomenology in that thing, you have to see a big space. So it seems to me that fine-tuning may be true, but it's useless. Because it will not give you a model in which you can do a calculation. I mean, I'm going away from, I don't care how you've got the model. You've given it to me. I still don't think you can do any calculation. So then it's not a model of physics.
Even if you can't do an exact calculation, can we say something about the statistics? Like you might ask about the distribution of that or something like that. So from these studies, could you somehow extract what's the distribution of?
So one thing you could do, so there's a million standard models. You can calculate using Yukawa couplings and energy effective action, the principle in these million models, and then see statistically what these couplings are, and try to make some statements there. My expectation is that none of these million models will be the standard model. I'd be very surprised if this is true at a generic point in moduli space. And this is leaving aside the issues of moduli stabilization and so on, which are separate considerations. So I'm skeptical that it's easy to find even one successful standard model, even with supersymmetry. But if I find one, I can probably find millions. So it's a question of either zero or lots.
What does it mean when you say find a standard model with supersymmetry?
I'm talking about these constructions here with the right hierarchies for the masses.
Yeah. So do we know how easy it is to find things with hierarchies within this set of?
So there was a recent paper by Lucas and collaborators that had a couple of examples of what they called, mass hierarchies, replicated mass hierarchies in standard model. They were looking at a particular class of non-abelian vector bundle, which is a sum of line bundles in this story. It's also not the most generic thing. It's also not most of these million models, but they had a few examples where they found isolated points in moduli space with the right hierarchies. So there's some proof of principle that in this class of examples, there is these hierarchies, but it's not moduli stabilized. So it doesn't count, in my view. I think that's the next step that you need to do in order to have a real theory.
Somewhat broad question.
Yeah.
What do you think some of the other areas where machine learning would be applicated? It's a very broad question. We can have more discussion over lunch also.
Right. So I think if you're finding a hard solution to a numerical to a different equation, let's solve numerically, machine learning is a good tool to use there. So for example, one of the things I've had some students looking at is these black ring solutions in 5D. They're known analytically in flat asymptotopia, but they're not known analytically in ADS or the sitter space. You can imagine looking for solutions to Einstein gravity in higher dimensions by just solving some coupled set of differential equations numerically, and seeing whether these numerical solutions to obtain from machine learning compared to the shooting solutions people looked at in other contexts. That's something you could do, for example. people are looking at Navier-Stokes, for example, trying to see whether turbulence is there's a deep mind paper maybe a month or so ago on looking at not the Navier-Stokes equations, but similar equations, and trying to look for stability of solutions there. So this idea of physics of neural networks is ideal because you choose a loss function, which is your solution. You try to zero in on the locus of your solutions to minimize that loss. So that's a tool you can use. If you want analytic results, you do things like we've done here for polytopes. Use these vectors in order to find things that, again, maximize or minimize some fitness score. Those are, you can pose the problem in a way that's amenable to these techniques, and you can solve various problems this way. Things like knot invariance we've looked at. The correlations between knot invariance, you can sort of experimentally find these by using machine learning, neural networks.
And this is useful for Bootstrap program.
So Kostas Papagiorgakis and collaborators have had some papers on using essentially feeding in things up to some level and looking at predictive correlators based on data you feed in. So you can imagine doing Bootstrap this way.
No further questions. That's time.
Thanks, it was a lot of fun. Great having lots of questions.
It was great talk and very impressive.